Dear students, welcome to another session of Nuclear chapter. Today what we are going to see is about nuclear reactor, which is actually the continuation of the previous class, the chain reaction. So you have seen like two types of chain reaction. One is controlled chain reaction, another one is uncontrolled chain reaction. And I also told you where actually this controlled chain reaction occurs and also the uncontrolled chain reaction. Controlled chain reaction usually happens in the nuclear reactor where we produce energy, and uncontrolled chain reaction, it actually occurs in the nuclear bomb. Okay, so we will see how this controlled chain reaction can be utilized to get energy from the nuclear reactor. So for that, what we need to know is the different parts and other thing which is required for this nuclear reactor. First one, so you can refer the diagram from the textbook, okay, and it will not be asked, diagram won't be asked for the exam, but maybe some concept will be asked for 1 mark. Okay, that's the reason why I'm giving you some brief idea about this nuclear reactor. First thing, nuclear fuel. So usually we are going to use uranium-235 as fuel for this nuclear reactor, and these uranium-235 will be embedded or filled inside in the form of pellets in the fuel rods, and these fuel rods will be dipped in the nuclear reacting chamber. Okay, it will be allowed to enter like using the machineries. Those fuel rods will be immersed into the nuclear reactor. Then what we need is the fission process should occur, right? For the fission process, I told you, giving an example of apple, saying that we need to have neutrons to break this uranium-235 and make it unstable. So what we need is not the fast moving neutrons, we need slowly moving neutrons, right? Or we need thermal neutrons. So how to slow down these neutrons? It is not possible just by keeping something. Okay, that's the reason why what we are going to use here is moderator. So moderator may be graphite or heavy water which is filled inside this nuclear reactor, which are going to make these neutrons, fast moving neutrons, to get slowed down. Then this slowed neutron, it is actually going to cause a nuclear fission reaction. When the fission reaction takes place, what happens? The uranium-235 becomes unstable and it de-excites, producing barium and krypton, you know, right? And those barium and krypton, they are actually radioactive, okay, along with the emission of 3 neutrons. Those 3 neutrons are actually causing the chain reaction, correct, right? Then what we need is a control rods. Why we need to use control rods? Usually used to have the cadmium material. So these control rods are used to control the fission reaction or to absorb those excess neutrons. Okay, I told you in the last class about the neutron multiplication factor. Okay, so there what we need is a protection of neutron and the loss of neutron. So it has to be balanced, right? To balance that, we will be using control rods to absorb the excess neutrons, so that the fission process will be happening in a controlled manner. Then what we need is a coolant, you know, right? So during this fission process, a lot of energy will be released. Okay, so those energy is obviously in the form of heat. So to control this heat energy, you need to use coolant. So coolants are like graphite can be used, okay, then pressurized carbon dioxide or liquid sodium, liquid potassium or heavy water. So if you observe, usually these nuclear reactors will be situated near the sea, the ocean. Why? Because so you can access a lot of heavy water. So whatever water which is there in the sea is heavy water, right? It is not the soft water what we drink. So this heavy water will also have higher temperature, this one boiling point. So this heavy water will be forced to come inside the nuclear reactor using some channel, okay, and the heat will be removed from that. That's the reason why usually these nuclear reactors are observed near the sea. Then the safety system. So safety system is must, correct, right? So what we are making use like a thick concrete walls, and inside that the thick lead bricks will be fixed, so that the whatever radiations like alpha, beta, gamma comes out of this nuclear reaction will be absorbed, and the surrounding area or the nature can be protected. Okay, so these are the basic idea about nuclear reactor, and you might get any of one mark question. Next one, what we are going to see is about nuclear fusion reaction. So in the fission reaction, we have seen like a heavy nucleus splitting into two lighter nuclei, right? But fusion reaction is an opposite process where two lighter nuclei combine to form a heavier nucleus. Two lighter nuclei combine to form a heavier nucleus. So the definition says that the process of combining two light nuclei to form a heavy nuclei, I think there must be mistake. The process of combining two light nuclei to form a heavy nucleus with the release of large amount of energy. So here two light nuclei combines to form a heavy nucleus. Okay. So here in this process you can see that a lot of energy is released. From where this actual energy comes? Energy comes from the mass defect. The mass defect actually here, the sum of masses of this two light nuclei is greater than the mass of the nucleus formed. What happens to the mass? Extra mass. It actually gets converted into energy, and we can understand with the relation of Einstein's mass energy relation. And that's the reason why we are getting lot of energy from this fusion reaction. So let me take the example over here. Let me take two hydrogen nuclei, or these are deuterium. Okay, these two combined to form a tritium along with a protium. Then 4 mega electron volt of energy is released in this process. Then this tritium again combines with another nucleus of hydrogen, or we call deuterium, and it gives a helium nucleus and a neutron, and with the release of 17.6 mega electron volt of energy. So in this total process, how much energy is produced actually? We can just find it out by adding this one. See, 17.6 plus 4 mega electron volt. So in this process, okay, this simple process, we are going to get energy equal to 21.6 mega electron volt. So this nuclear fusion reaction is not actually possible in the reactors. It is very difficult because to combine these two nuclei, lot of heat and high pressure is required. Okay, so the fusion process actually occurs in the sun or any star, because it requires very high temperature and very high pressure. Okay. Now we will see about one more fact about this nuclear fusion, that energy released per unit mass in the nuclear fusion is greater than energy released per unit mass in the nuclear fission. So energy released per unit mass. So let me have some mass. Okay. So energy released with respect to this mass will be greater for the fusion reaction compared to the fission reaction. That means with lesser mass we can have more energy with the fusion reaction compared to the fission reaction. Okay. And the final product of fusion are not radioactive. See, this is the greatest advantage what we have, because the fission reaction, whatever we get, barium and krypton, so it has to be preserved. Okay, otherwise it will cause some kind of problem with the nature. But here it is safe actually. The byproduct whatever we get here is not radioactive. And it is the main fact why we don't have this nuclear fusion reactor. It is a problem of obtaining that much high temperature. Now we will see where actually this nuclear fusion takes place. One such fusion is known to be thermonuclear fusion. So thermonuclear fusion is nothing but the nuclear fusion achieved by rising the temperature of a substance so that the nuclei have enough kinetic energy to fuse. So thermonuclear fusion is nothing but we are heating a substance, okay, in such a manner that its nuclei will have certain amount of kinetic energy so that they can fuse together. That is known as thermonuclear fusion or fusion process with the help of temperature. Okay. Next one is about stellar energy. So stellar energy is actually energy obtained from sun and other stars. So stellar energy is simply known to be the energy whatever we get from stars and sun. Now, how actually the energy produced in the stars? There are two types of cycle reaction takes place. One thing is carbon nitrogen cycle, another one is proton proton cycle. So you know what is fusion? Fusion is nothing but hydrogen nuclei combined to form heavier nucleus, right? Now for this process to happen, you need some catalyst. So in chemistry you know what is catalyst, right? Substance which helps or to make helps to speed up the reaction. Similarly, here in this reaction we have two catalysts, one is carbon, another one is nitrogen. Now we will see how actually this reaction takes place. A carbon-12 combines with a protium, or you can say the hydrogen nucleus. It is going to give you N13 with the releasing of large amount of energy, and this is not actually stable. This is not stable. What happens? This N13(7) it becomes C13 and one positron, and also lot of energy is released. Now this is actually stable. C13(6) is stable. It again combines with another hydrogen nucleus to form unstable N14(7) with the release of energy. So this is actually stable. N14 is stable. This N14 again combines with another hydrogen. It is going to give you unstable O15(8) with the release of energy. Again this O15(8) will give you N15 plus one positron, then lot of energy is also released. Now this again combines with the N15 combines with another hydrogen. It is going to give you C12(6) plus one helium nucleus, and again lot of energy is released. Now let's try to check the equation by balancing it. We can see here right hand side has to match with the left hand side, so I can cancel this one with this, correct? Then O15 over here, then N14 over here, C13 and this one. Now what we are remained with? On the LHS we remained with the 4 hydrogen nucleus, okay, 1 2 3 4. So we can write 4H1. That gives, on the right hand side what we have is energy, okay, then 2 positron, see here, then 1 helium nucleus. So He4, then 2 positron plus 26.7 mega electron volt of energy. So this is actually an assumption that this much of energy is released, okay, and this value may not be the exact one but nearly the same value. One more cycle, it is about proton proton cycle. Here you can see like 2 hydrogen nuclei combines, and you are going to get here a deuterium and 1 positron with the release of energy. Again in another process, this deuterium gets added with another hydrogen. It is going to give you like a He32 with the release of energy. Then 2 He32 will combine to get a helium, okay, and 2 hydrogen with the release of energy. So in this process we can get here the same equation what we are going to get after cancelling everything, that is 4 hydrogen will give you He2 like helium nucleus, then 2 positron plus 24.6 mega electron volt of energy, okay. So these are the two processes, and it may not be asked for your examination. You can just to keep in your mind, and you can try to solve the equations. Okay. Okay, now we will see some problems. Okay, numerical problems related to this chapter nuclei. Actually, I already solved some two problems related to the other topics. Now we will see the problems which were appeared in the previous year's examination. One such problem is determine the mass of sodium which has activity 5 millicurie and half-life of sodium is given to be 2.6 years. And they have also given us that the Avogadro number is 6.023 into 10 to the power 23. Now first what we have to do is we will just write the solution where note down all the given terms. Given T half, that is half-life, is 2.6 years. So it has to be converted into seconds. You know, right, how to convert it? We will multiply by year, number of days, that is 265, then 24 into 60 into 60. So value what we are going to get here is 8199 into 10 to the power 4 seconds. So this is a value of T half. Keep it aside. Next one, activity. Activity is given to be 5 millicurie, right? So what is milli? It is 10 to the power minus 3. Then curie has to be converted into becquerel by multiplying 3.7 into 10 to the power 10. Now we get the value of this. If you want, you can solve here itself, otherwise you can just keep it. Now our intention is to find mass, right? For that we need to find out activity first. To find activity we need the value of decay constant. So from equation of half-life we can find out decay constant, because we know, right, it is just 0.693 divided by decay constant. Take the term to the left side, take this term over here, then substitute the value. Lambda is equal to 0.693 divided by T half, that is 8199 into 10 to the power 10. So do the calculation, you are going to get a value 0.8452 into 10 to the power minus 8. Okay, in terms of second. Now activity can be calculated with the formula A is equal to n lambda. Correct, right? Remember this, n lambda. So this must be per second. N lambda. Then n is equal to A divided by lambda. Just rearranging this equation. We know what is A. A is already here. It is 5 into 10 to the power minus 3 into 3.7 into 10 to the power 10. That's the same thing what we are going to substitute it over here. Then lambda, we have already got the value. We can just substitute it over here, do the calculation, the division, then you are going to get the value for n, that is equal to 21.88 into 10 to the power 15. So here you can see in 22 gram of the substance you are going to have Avogadro number of molecules, right? Then in this mass, like 21, so how much mass we will have when you have number of particles 21.88 into 10 to the power 15. So to find out this m, you can just cross multiply. So 22 into 21.88 into 10 to the power 15 divided by Avogadro number. So while doing the calculation you will be arriving at a value m is equal to 79.92 into 10 to the power 8 gram. So this is what the mass of the sodium, which has activity 5 millicurie and a half-life 2.6 years. Okay. So try to solve the problem by your own. Now we will move on to another problem to determine. So the problem is given like determine decay constant and half-life. But we are given with is the activity of the substance. Initially it is 4700 per minute. 5 minutes later the activity becomes 2700 per minute. Now you have to find out with respect to this activity, you have to find out decay constant and half-life. So we will list out first the given terms. A naught is given 4700. Then A, after time t, that is 5 minutes, you have 2700. Now activity, we know the formula for that. From the decay law, we can write A is equal to A naught e to the power minus lambda t. Just rearranging A divided by A naught, that is e to the power minus lambda t, correct, right? Then reversing this equation, A naught divided by A, what happens here is this negative sign vanishes. You will have e to the power lambda t. Now you have to take log on both the sides. So log is actually, I gave you the idea of ln, that is equal to log to the base e, that is also equal to 2.303 into log to the base 10, correct? Now we will take ln on both the sides. So ln on the left side and as well as right side. So when you take ln on right side, what actually happens here is this exponential term vanishes. Then what you remain with, you can take t to the other side. So what happens, lambda is equal to 1 by t. See, just taking t to the other side, it goes to the denominator. We will write it as lambda is equal to 1 by t into ln A naught divided by A. Now you can write from this lambda is equal to, what is this ln actually? I told you already. We will write for this one. So 2.303 into log to the base 10 A naught divided by A, 4700 divided by 2700. So do the calculation, okay, do this, take the log of that, then you get these values. This t is nothing but 5 in terms of minute we are finding. Substitute the value, get the answer for lambda. You can get the value for lambda. Then after getting the value for lambda, you can write t half, that is equal to 0.693 divided by lambda. So do the calculation, okay, then you can get the value as 6.249 minutes. Okay, this is the answer what you are going to get. Problem number 3. So try to do the problem, okay, solve it by without referring the class. You can solve it by your own using calculator and a logbook. The third problem, calculate t half and mean life of radium 226 of activity 1 Curie. So what we are given with, mass of radium 226 is given to be 1 gram, it is 1 gram, and 226 gram of radium consists of Avogadro number of atoms. So this is given. Now first what you have to find out is the number of atoms you have to find out. For that you have to substitute the value over here. N is equal to 6.023 into 10 to the power 23 divided by 226. Okay, that is a mass number of this radium. You have to divide it. Then you can find out activity using the formula lambda n. Then lambda is nothing but taking the term to the other side. Then t half can be found after finding lambda. Then mean lifetime can also be found just by dividing like 1 divided by lambda. So this is a homework problem. You have to solve this and you have to send me the answers.